another commonsensical theorem, and this is something that we already used as well. So if you have an object and you have some work that you do on it through the force, of course. So the theorem tells that if I do more work, okay, so we have two cases. So here I do work 1, here I do work 2, and here I do work 2. If work 1 is greater than work 2, in the first case I happen to do more work compared to second case, the kinetic energy gain over here will be more than the kinetic energy gain over here. The change in kinetic energy will be more over here than over here. Is this right, or is this opposite? Or is this right? Was that right, or is this right? Think, use your common sense. The first one was right? So first one is right. More the work I do, more the kinetic energy change I will see. And that is your work energy theorem. The work we do on an object is directly tied to how much its speed increases. The more work you put in, the faster it goes. That's the work energy theorem in a nutshell. The net work done by all the forces acting on a body is equal to the change in its kinetic energy. As simple as that. Of course, there are a lot of preconditions, but in general, if I happen to do some work and we see gain in its motion or gain in its speed, then the work that we do, the force we put and all of that, that has got converted into kinetic energy, right? So yeah, related maths, when we have constant force and we have variable force, actually that's supposed to be the proof. I didn't write the heading right over there. Proof of work energy theorem. Case constant force. Okay, so we have a constant force applied on a body of mass, say m, and this is constant, right? So it of course it leads to some kind of acceleration if it starts moving. So we have some kind of acceleration, or if we are getting any change in the velocity over there, it has some acceleration. Say it covers a distance of s. Okay, so let me do that properly. So it covers a distance of s, and the body changes the velocity, say from v to u. So with all of this in mind, we can rewrite this as v square is equal to, not rewrite, sorry, we can relate all of this as v square is equal to u square plus 2 into a into s. Now I will multiplying, what should I multiply? Think about it. I'm trying to relate it to kinetic energy. See, every derivation is commonsensical. What should I multiply over here? Go back to kinetic energy equation. It's half mv square, right? So what should I multiply with? Half m on both sides. So what we have here is half m v square is equal to half m u square plus m into a into s. Okay. Now what does this look like? We already told you guys, this is your kinetic energy final. This will be your kinetic energy initial. Plus, what does this look like? Mass into acceleration is force, force into s is your work. Therefore, work is nothing but kf minus kef minus kei, that is change in your kinetic energy. So change in the body's kinetic energy is the work done by the net force. right guys? So that is your first proof. But what if I don't have a constant force but a varying force, right? I think the second case is variable force or varying force. Again, let's consider a force. Let F a varying force, right? So act on a body of mass, okay, no comma over there. M, and let it produce a, actually, okay, and produce a displacement of, say, ds, sorry, right, in its own direction. Okay, so the small work, therefore the small work done by F will be what? dW will be equal to F dot of ds, right? But theta is 0 degree because it's in own direction. So this will be F into ds. We have done this actually. Then what do? Then we multiply, sorry, then we rewrite F as m into a and a as dv dt and ds. So m dv ds by dt, and this is nothing but your velocity. So the small work that we get to see can also be expressed as mv dv, momentum times the change in velocity. So this is what we'll get to see. Okay, so as a continuation, so if the applied force, it increases the velocity from say u to v, then the total work done will be, how do you find it? Using integration. So if the applied force changes the velocity from u to v, right, then the total work done on the body or on the object, whatever you want to call it as, will be integration of the expression mv dv. So m is constant, v is what is changing, so this will be v square by 2 u to v. So I'll take half out, and this is v square minus u square. Okay, don't get confused with this v and this v and all of that. They're variables and these are values. So I can even call it as x to y also, doesn't matter. But if I expand this, I'll get half mv square minus half mu square. This is nothing but kinetic energy final minus kinetic energy initial. And that's what your work energy theorem tells, that whatever work we do, see, that's the final answer. Can you see that? Whatever work I am doing, that is changing purely into change in the kinetic energy of the system. And that's what the theorem talks about, right? So a small recap. This is something that I want to put it across. Some of the point might not be, might not make sense, but understanding is what I aim for, right? Now, precondition for applying work energy theorem. So what is that we are looking at? We are looking at particle being rigid body. So there's a definite definition for rigid body that also we'll be seeing in the next set of chapters. A body must be treated as a particle or a rigid body, that is no internal deformation or rotation unless accounted for. So when you apply it purely, it is changing the object's kinetic energy is what we are trying to tell. So of course, when you press something, you have seen this, when you press something, what happens? There's a bit of deformation, whatever you do. There's a bit of deformation, right? When you touch a ball, when you try to hit a ball, there's a bit of deformation. When you, in baseball, when you hit a ball, like there are many slow motion videos wherein you get to see how much it bends, right? That is not happening in our case. So in our questions, in our derivation, net force is known, displacement is measurable, okay? And the fourth point is classical regime, that is speed involved must be less than the speed of light. So we can't talk about that, anyways, we won't deal with that. No energy loss unless modeled, that is if friction, air resistance and other non-conservative forces are present, then that has to be excluded. So yeah, all of this, few of them might make it sounds like a bit of commonsensical point. Few of them are out of syllabus and stuff, but yeah, on and off, I think we'll use few points over here. So case by case, I'll take up and explain it. Again, my explanation are not going to end with any theory part. It always carries over to numericals. Actually, pretty much everyone teaching physics, it's so. Theory itself will not make sense. It makes sense with numbers because we understand numbers better, most of us, than variables. Right, work energy theorem, it tells what we understand. If I do a work and we get to change some velocity, the change in velocity has to be in terms of, the gain in velocity or the gain in kinetic energy has to be related to the work that we do. More the work we do, more or faster it will go, as simple as that. That's all the theorem tells, right? So you should copy this. And we proved it for two different conditions. You need to write those headings and yeah, copy this.